There's another particle experiment which is British, and this has to do with the density of the dust. It's fascinating, but it does raise a problem, because it's this dust which is the greatest threat to Giotto's survival. James.
Well, there's now less than an hour to go and 231,600 kilometers to go to closest approach. As you can see on the left, there's time to go to the closest point, and on the right, the distance. And from here on, from this distance out, to the problem of dust becomes the major test of the mission. The first impacts from the dust cloud in the Comet around Halley were predicted to start just a few minutes ago, and we've heard that that's exactly what's happened. Let me remind you of what's happening out there in space. Giotto is heading in towards Halley like this, with its protective dust shield forward, and I'll get back to that particular dust shield in a second. There you can see it spinning around with the dust shield leading. Now, the theory is that the dust I'm talking about happens as a result of the sunlight evaporating the icy surface of the nucleus of the comet and the explosion of superheated gas pockets in that surface, sending the dust shooting out in great fountains to spread perhaps as far as, 100,000 kilometers out round Halley. I say it's all theory because nobody knows. That's one of the things we're hoping to find out tonight. But the size of the dust particles in that maelstrom are known. They're anywhere from this size, the size of a dried pea, right down through sand grain size to tiny particles this size, so small that they almost smudge when you move them around, and beyond that to the size of the particles in the smoke from a cigarette. Now, those dust particles are killers for two reasons. The first is communication. You see, the main spacecraft antenna, this dish here, is sending all the data and the pictures back to the receiving dish in Australia, back on Earth, 130 million kilometers away. Now, the distance involved in that communications link is so great that it needs pinpoint accuracy for the antenna to make and maintain contact. 1 degree off, that much, and we lose contact. And an impact from one particle this size hitting the edge of the spacecraft could knock Giotto off-center enough for the signal beam to miss the Earth. The second danger to the spacecraft is less, shall we say, subtle. Particle impact could just destroy Giotto. That's why there is a dust shield, or rather, two of them. An outer shield here, 1 millimeter thick, made of aluminium alloy, like this. And an inner sheet, 25 millimeters behind it, itself 12.5 millimeters thick, a backup shield made mostly of bulletproof plastic laminate to take the force of the particles that are big enough to smash through the outer shield and hit this inner shield like in the form of a jet of high temperature vaporized material. And they're expecting plenty of that kind of activity. In fact, at worst, all the spacecraft has to do is just survive through that dust storm long enough to get in really close to the nucleus to snatch its pictures and scientific data before it is possibly destroyed. And if you think I'm overdoing the drama bit, take a look at this. This is a piece of test material looking at the conditions that forward shield would encounter, the thin aluminium shield. It's been scaled up because they can't shoot a pellet as fast as the spacecraft is going. So the whole thing's scaled up. This was made by a pea-sized object fired at 5 kilometers a second at this aluminium 8 centimeters thick, 8 millimeters thick. That is the same scaled-up effect of one pea-sized object hitting the forward shield, that thin 1 millimeter thick shield. Now, they're expecting many, many of these impacts, perhaps as many as 10,000 a second. The second test they ran was on the Kevlar, as it's called, the Kevlar backup shield. And here they used a laser to produce the kind of effect that the jet of high temperature plasma coming from the result of a particle having smashed through the front shield, the effect it would have on the Kevlar. And as a matter of interest, over here on the edge, there's a tiny detector. There are several of them around, as you'll see soon, that actually detect those impacts happening. And that was I was talking about when you were looking at the screen on which we will be able to show you the effect of those impacts as they happen because of computer generation. The key point encounter, as you can see on the countdown, will happen 51 minutes, just under 51 minutes, and 213,000 kilometers from now. There are, as you would expect, from what I've said about the dust, several experiments on board measuring those impacts. 2 experiments registering impacts by the very small particles, and one run by the University of Kent for the bits large enough to call what they're expecting to make real trouble. Tony MacDonald leads this British experiment. It's called the Dust Impact Detector, or DID. Giotto's leading surface carries 3 tiny sensors. The inner shield carries 1 more. The sensors are miniature microphones to record the impact of particles hitting Giotto faster than a bullet. MacDonald's main problem is that he doesn't know just how big the particles will be, and will the twin shields be enough to protect Giotto? He tests the system with tiny glass beads. The mini microphones record the impacts, telling MacDonald the size and position of Halley's dusty missiles.
At the moment, the experiment is going very well. We're getting a high-level activity on the front dust shield, and this is showing that some of the particles are going through to the rear, and it does so show that the meteoroid protection system is working. Looking at the next few minutes, we're going to find the activity increasing and several thousand per second later. What's important is that we get through the point of closest approach and come out of the comet on the other side.
So you see there from what Tony MacDonald was saying, they're already getting impacts that are going through that front shield. By the way, it's called the sacrificial shield, and now you know why, because even this far out, 206,000 kilometers with 50 minutes to go, they're beginning to get impacts going clear through that front shield. Well, the predictions are, in fact, that they will hit a fair amount of these medium-sized particles early on, and then hopefully the impact rates ought to drop off a bit before those rates start to rise inexorably towards maximum density as we move towards encounter. Question is, will Giotto survive long enough to get close enough to learn something about what that nucleus is made of? Patrick.
The nucleus is, after all, the heart of the comet, and that's what the scientists here are trying to study above all else. Up to now, we've been reduced to little more than guesswork. Some years ago, it was thought that a comet might be a flying gravel bank. But now there's good circumstantial evidence that the nucleus is an icy mass, about 6 kilometers in diameter, spinning round in something like 54 hours. If we knew the size of the nucleus, we could work out its mass and its volume, and we could then estimate how long Halley's comet will last before all its ices are used up. And present estimates range between 50,000 and 200,000 years. The camera was switched on again for the encounter 5 hours ago, and this is the best picture it's sent back so far. Well, dust or no dust, the camera is certainly sending back results, and there's quite a difference between this picture and the last one you saw. Now remember, Giotto is approaching the comet at something like 68 kilometers per second, and that makes a tremendous difference even over short periods. And now we can actually start to see structure in the comet. Once again, let me remind you that these colors are not real. They indicate differences in brightness and therefore differences in density. And there's no doubt that the densest and brightest part of the comet is that white blob you can see at the bottom, and that is where the nucleus is, even though we can't actually see the nucleus itself at the present moment. And then red, blue, green, and purple indicate lower and lower light levels. So at the present moment, the camera is sending back good results. And of course, as it goes in closer and closer, we shall get better and better results. And one thing we know, though, for certain now, the camera itself is working really well. James.
Well, this is where the camera sits, with its mirror poking out from behind the dust shield. That camera's job, of course, is to detect the nucleus and then take as many color pictures of it as it can. The delicate camera is Giotto's most immediately dramatic experiment. Already it's sending back a continuous stream of pictures. This is Giotto's eye, giving scientists the chance to see a comet's nucleus. The camera can be rotated to take pictures both ahead and behind Giotto as the spacecraft skims close to Halley. The hope is that the camera will survive the dust storm, mounted as it is behind the bumper shield. Its pictures in 4 colors allow scientists to establish the size and shape of Halley's nucleus. From 500 kilometers away, the camera can pinpoint an object a mere 30 meters across on the comet's surface. All this while Giotto itself is spinning 4 times a second. Incoming light, and maybe dust, bounces off a steel mirror into a telescope. The image is then focused onto two charge-coupled devices, or CCDs, which take the picture. This is what the charge-coupled device looks like. Hundreds of lines of light-sensitive spots, and as the spacecraft rolls, I'll use my finger to imitate that, and the image moves across the camera mirror, one thin cross-section of the image at a time is stored on here for a few microseconds, and the data sent back to Earth. And then the next line, and so on. It's hairy stuff, but that's quite a camera. I mean, it could, for instance, get a clear shot, they say, of a mole on the face of the pilot of a Concorde going by a mile away at the speed of sound, which is great if the Concorde isn't in the middle of a cloud, which, according to last week's Russian pictures, Halley is. Now, from 8,000 or 9,000 kilometers, the Russians weren't expected to see the nucleus. Even so, the cloud they did see looked very small and very dense. When all the Darmstadt scientists got together to discuss that particular matter, all hell let loose. Some wanted to send Giotto very much closer than the planned 500 kilometers. But the camera team naturally wanted to play it safe and steer clear to over 1,000 kilometers away from anything that would sandblast the motor of their camera. With 2 or 3 times as many camera scientists occupying far more space than any other experiments, it would have made it a waste of money to build a spacecraft that could go to half that distance, to 500 kilometers. So in the best European tradition, they compromised. They chose a target distance the other day of 540 kilometers, almost exactly what had been originally intended. Just now, as you can see, the distance to go is 185,000 kilometers with just under 45 minutes, and closing. What are the pictures like from this distance? Patrick?
Well, they're pretty good, and the camera is working very well. But one thing we have got to remember, as Giotto goes into closest approach, it makes a very, very rapid pass of the nucleus, only about 10 seconds or so. And altogether, Giotto spends only about 4 minutes closer into the nucleus than Vega did. So it's got to be a very fast business altogether. But all the same, they seem fairly confident that they will get better pictures than Vega obtained. The procedure, by the way, is for Giotto to send back a raw picture, and then, after a few minutes, it's enhanced. So you get a bigger and better view of it. And that's the way it is done. And all the pictures you're going to get tonight will be on this false colour principle. And I say again, the colours are not genuine. But already the comet is showing structure. And as we get closer and closer to the nucleus, there's no doubt at all that these pictures will gradually improve. So is the nucleus really a dirty snowball? That was the theory put forward by Dr. Fred Whipple over 30 years ago. You're still confident about it?
I certainly am. I think we have a great deal of evidence to prove that it is true. Particularly radar observations, radio reflections from the nuclei of 4 comets showing that there is a discrete body in each one of them.
What evidence are you looking for from Giotto?
Well, particularly the shape and the surface characteristics of the nucleus, because so far this has been entirely a matter of imagination. Now we will see the real thing.
So you're really hoping to see the nucleus tonight?
I'm really expecting to see it tonight.
Well, some people suggested that we won't because it'll be hidden by dust.
Well, there will be some loss of visibility due to dust. There's no doubt of that. But I think that because of the protection that the camera has in Giotto, there's a good chance that we shall see at least some details of the nucleus.
If we're going to make really close-range studies of the nucleus, the first thing we have to decide is exactly where the nucleus is. And remember, it's well and truly hidden by the dust. There's another complication also, the jet problem. Gases escaping from the nucleus which push it around and may also be a hazard to Giotto. Dr. Rudiger Reinhardt. Could they possibly endanger the Giotto mission?
They could very well endanger the Giotto mission, although one has to say that the dust jets as we see them consist of dust particles in the range of 1 to 10 microns. These particles are of no danger to the Giotto spacecraft. However, associated with these visible jets are regions of dust particles which are not visible, large dust particles, and these could endanger the Giotto mission.
Could they put it off course?
Not off course, but they could disturb the spacecraft attitude, and then the telecommunications linked to the Earth could no longer be maintained.
Well, here I am with the guests. Sir Francis, you've been watching what's happening so far and listening to the people in Darmstadt sounding as if everything seems to be nominal, although those pictures are quite remarkable. What do you think about the chances of the mission?
Oh, that's just sheer speculation. I'm just sitting here and enjoying the atmosphere of the whole occasion. I mean, here we are sitting in the room where Halley worked for 20 years or so. I'm seeing on the monitor people like Jan Oort and Fred Whipple, who have done so much, if you like, speculation, but marvelous ideas, marvelous theories about the comet. And we're just sitting here waiting for it to happen. I think it's wonderful.
Yes, it is, as we've said already, of course. It's a once in a lifetime for almost all of us, isn't it? Professor Meadows, this business about the dust, it doesn't seem, it seems to have been a bit of a blip and then it's quietened down. Is that what you would have expected?
Well, like Graham, I'm in a coma. Sort of, I think, is the answer. If you look at the Vega results, which you've seen earlier, yes, they were actually somewhat discordant. And the problem is that the theme tune for any comet is ashes to ashes, dust to dust, hurry on, baby, you must, if you follow me.
That's a technical statement.
It's a technical statement which will be published in due course. The problem is that they're erratic. They give out stuff. You were talking about jets there a little while ago. The problem is you get these jets erratically, you can't predict them.
Yes.
And the stuff you can see is the smaller stuff, ground-based. Unfortunately, ground-based, you can't see the larger stuff, and that's the dangerous stuff. Which
and
is
in fact, there've been, a number of impacts through the front shield already.
Already, indeed. The problem is the size distribution can't be accurately predicted from Earth because you only see a part of it.
So you can't fully prepare for it. In other words, they can put up a sacrificial shield, but presumably it is impossible to say that a large enough particle will not come along that will go right through the spacecraft.
Spot on, right.
Is that possible?
Oh, of course it is, yes.
And you have no way of predicting?
No, because where you're dealing with a small number of large particles, then you're dealing with small number statistics and you cross your fingers.
Yes, sure. And there's a lot of space out there. Let me turn to Alec Boxenberg. You kind of pioneered means of seeing clearly at great distances in space with your work on the image intensifying systems earlier in the last decade, in the middle of the 70s. What's your view of the pictures coming in now?
Well, they're remarkable pictures. The device that's used is the charge coupled device that you mentioned. Yes. Now, that has an extremely large dynamic range and, of course, is very sensitive and has a very wide color response. And all those things coupled to give immensely high quality. But, of course, you can't see that necessarily immediately.
Yes.
These pictures have to be massaged.
You think we'll get a good picture of the nucleus if it gets to see it?
Well, I think we'll get a good picture eventually. We may not see that tonight, but we will be able to massage that picture and see it eventually, I'm sure.
Good. Thank you very much indeed. I'll come back to you, of course, later on as the mission proceeds and we discover that everything you've said is wrong, all of you, including us. Let me go on now to talk a bit about the origin of comets, because where comets actually come from has always fascinated astronomers from long before the time of even Halley himself.